Hello everyone, I am Francesco Cameli and I'm here to talk about Omni, which is a domain-specific language for audio programming that I've been developing in the last 7-8 months. So before we talk about that though, we need a little bit of context about my work maybe, because what I want to stress out is that I'm not a formal computer scientist. I had no formal computer science background, and in fact I'm a composer and improviser, so a musician. And what I'm doing right now actually is completing my master's degree in music at the University of Huddersfield in the UK. And Omni is actually part of the submission for my master's thesis. So if you want to get in touch with me, these are my contacts. Feel free to ask me any question regarding Omni or whatever other project I'm working on. So before we talk about what Omni is, we need a little bit of an introduction maybe about digital audio and how that works. So digital audio is a real-time process. What does this mean though? So a real-time process is a process where the processor of your computer has to meet specific deadlines. In the case of digital audio, these deadlines are determined by two factors. One is the sampling rate, and the second one is the buffer size. What are these though? So let's take a look at this picture. On the top, you can see a continuous signal, a continuous sine wave. Think about it like electrical current. Electrical current voltage does not flow in discrete value. It flows. That's how you express about it. So it's a continuous state. In a digital system, however, you need discrete points in time where your processor is actually doing at specific frequency its processing, its calculation. That's determined by the speed of your processor. So to go from a continuous signal to a discrete signal, we need to sample it. This is the term that it's used. Sampling a continuous signal to a discrete signal means basically taking a snapshot of individual values over time at the same distance between successive values. The amount of these samples, that's how they're called, that we're taking per second is determined by the sampling rate. So in this case on the bottom, we're actually having a sampler rate of 20. So we're having 20 samples per 1 second worth of audio. It's quite low actually. Common values are much higher, starting from 44,100, which is the standard for CD, for the CD standard. 48,000 is another one, and they go all the way up till 192,000. So 20 is quite a little number, but if you think, if here we had 48,000 instead, you see that you would get a better and better approximation of your original signal. So the more the sampling rate, the more accurate representation we can do of a sound. Your processor is actually computing this sample at specific intervals. These intervals though are not controlled, the deadlines are not sample by sample, because there will be too many interrupts for your processor to handle. If you think about it, 48,000 interrupts in a second just to calculate one sample that could go through a lot of process, it's quite expensive. So the way we deal with this in digital audio is to divide the samples into chunks. So for example, and this is the buffer size. So for example here, let's pretend we have a buffer size of 5. This means that we're gonna have a chunk of audio of 5 samples at a time to process. And while we process that, our audio interface might get new chunks giving us those chunks when we return the one that we just calculated, right? So it's a process of getting stuff from the audio interface, calculate, so fill the buffer, giving it back out in time before you get the new one. If you lose a deadline, if you miss a deadline, you're gonna get bad events, usually audio drops. So this is just to get a little bit of context around this. So how do you do audio though in digital systems? Usually there are the two most important paradigms will be programming environments on one side and digital audio workstations on the other. Programming environments are more low level generally, and digital audio workstations are a little bit more higher level, but they serve different purposes. Example of programming environments would be MaxMSP, Pure Data, SuperCollider, CSound, Chuck, among others. And example of DAWs, digital audio workstations, would be Ableton Live, Reaper, Cubase, Bitwig, Pro Tools, etc. So what are the differences? So in programming environments, the way you treat sound is by connecting things together, usually. That's called patching objects. So you don't have a predetermined way of dealing with sound, but you determine it as you go. You program your sounds, you code them in a way. In digital audio workstations, everything is more higher level, where the only thing you can actually change is the mix of the different tracks. So imagine as your tracks as being the different instruments you're using for your composition. So drum track, bass track, synthesizer track, etc., etc. And you mix them together and you apply some effect to create certain effects. Like, I don't know, you can apply delays, reverbs, distortions, etc. To that. But the way you compose music is by dealing with a horizontal timeline, pretty much very similar to what you do in video editing software. In programming environments, on the other hand, you're not stuck with any predetermined way of composing. There's no horizontal timeline. Well, you can impose it, but it's not imposed by the program itself. So, some example programming environments. Here we have MaxMSP, and you see here what I was talking about. You have this little squared objects, that's how we're calling Max, that you connect together to these patch cables to create your signal flow. On the other hand, a digital audio workstation like Ableton Live, as I said, works by layering tracks on top of each other. So here we have a drum track, a bass track, a piano track, etc. And you apply effects on these tracks. Usually these effects are expressed via the standard of virtual instruments, VSTs, which can be either developed by the people who develop the DAW themselves or external developers. So it's a way of extending the capabilities of your DAW. But the difference, again, is that VSTs, for example, are pieces of software that do that one thing, and they kind of have a black box approach. On the other hand, in programming environments, you actually can build those effects and those things from the ground up, and you're not enforced to use, the horizontal timeline paradigm. Other example of programming environment would be SuperCollider, which is the one that I'm going to be using today to showcase some stuff, which is a textual programming environment. And another example of a DAW would be Reaper. As you see, he has the same approach as Ableton Live. You still have tracks, a mixer to mix tracks, VSTs, etc. So, what is Omni then? Like, why are we talking about this stuff? Well, usually when you want to develop new objects for your programming environments, new virtual instruments for your digital audio workstations, you need to have quite a deep understanding of C and C++. That's how you usually develop your extensions to these environments. But I realized that, especially when you're prototyping or where you actually want to get stuff done quickly, you don't always want to go to C++ and C. So Omni serves this purpose exactly. Like, it's a minimal and easy to use domain-specific language to express audio algorithms, and then will work cross-platform and cross-application. So you will write the code once, and then if a wrapper has been developed around that code, more about the wrappers is coming later, it will work on any application. So you write your code once and use it everywhere. There are similar projects out there. Sorry. One of them could be Gen, which is proprietary by Cycling74, which are the people that make MaxMSP. It's very good to rapid prototyping. It's embedded in Max, but it only works in Max actually. It exports to C code, but the C code is not plug and play. It's just you have to then take the C code and do a lot of stuff with it before actually making it usable for something different. And also the main problem I have with Gen is that it presents the programmer with fixed data structures. So here, for example, this delay object you see here, it's, let's say, is the lowest level you can get in Gen. You cannot define what the delay is, if that makes sense. You're stuck with the objects, with the functions that MaxMSP and Gen give you. Another project which is similar in scope to Omni would be Faust, which is developed at Gram in Lyon. Sorry if I pronounced any of that wrong. It's a functional programming language for audio streams, and it's very similar to Omni. Like, it's still open source, it's cross-platform, cross-application, it has multiple exports. So what are my problems with it? Well, not really problems, but I'm not a huge fan of functional syntax. It's just me. And also, I found Faust to be quite a monolithic project where all the external contact with the world, like the compilation of Faust code, all the different exports you can do, like standalone BSD, MaxMSP, SuperCollider, etc., are all embedded in the Faust compiler. So it's this big monolithic compiler that then exports out. While my idea mainly is to have a minimal compiler, the Omni compiler, and then you would want to write wrappers around that to make them export that code to other environments. So this also stimulates not just me but other people to develop their own wrappers for their own specific projects. And also it also means that I don't have to maintain stuff that I don't care about, maybe. I think that's one of the worries of all developers. So again, I was not satisfied much with the tools that were out there, but I'm not skilled enough, I'd say, to build a language from the ground up. Like, maybe I would get to that level, but it would take me a lot of time, and I need to make music. That's what I do. So what's the solution for me? Well, for me the solution was meta programming. I started looking at Lisps and Julia, but never quite clicked with me. I didn't like the way that you would compose meta programming. It never felt like a new language. It always felt like weird dialects of another language. But Nim, on the other hand, has amazing meta programming capabilities that literally lets you manipulate everything about its abstract syntax to you, and also create your own syntax for things. So what does Omni code looks like? It looks like this. It's code based around the concept of blocks that introduce new scopes, and each scope has a specific feature or property regarding the creation of your audio algorithm. Again, here you can also code your own data structures. We're gonna look into those later. And also, Omni gives you the certainty of having memory safe code, in the sense that you never, all the allocations that you do, for example, will have to happen in the init block, which is where you allocate memory. We're gonna talk about it later. And if you do it anywhere else, you're gonna have compilation error, so not a runtime but a compilation. And also, every memory you allocate is going to be freed for you when you don't have to worry about that. Basically, it's going to be freed for you. So the first block is the ins, and the first two blocks will be the ins and outs blocks, which determine the number of inputs and outputs for your algorithm. You can also express names for your inputs and outputs, and default minimum and maximum values for your inputs, so you don't have to worry about stuff getting out of bounds, for example. The init block, as I said already, it's used to initialize variables and initialize structures, which is the way in Omni to have your own data structures. In this case, for example, here we're allocating a delay, which is an inbuilt struct in Omni, which declares a delay line. But also, what's this build block? Well, the build block basically passes on to the next scope, which would be the sample or perform blocks, specific variables. For example, you might not want to use this delay length variable anymore, and you just use it to initialize some stuff, and you don't want to carry it over. So you put what you care about in the build block, because otherwise, if I didn't have the build block here, all the variables declared in the init block will be passed on to the next scope. What's the next scope? Is the perform and sample blocks. Those two are actually the core of your algorithm, and happen at different levels. So the perform block happens at the block level, as we talked about, the buffer level, while the sample block actually operates sample by sample. So in the perform block, usually you might want to initialize some variables, some states that you want to maintain throughout the whole block, and in the sample block, instead, you want to just, implement your algorithm, if that makes sense. Here it's just a simple delay line. We're going to look into this actually now in the live demo. Surprise, surprise. So first of all, how would you install Omni? Well, I guess we will use our favorite package manager, Nimble. So we just Nimble install Omni, and you're good to go. Right. let's write some Omni code. So here, let's save this as omnisine.omni. So we're gonna code sine wave oscillator. So here in VS Code, I also have an extension for Omni. You just search it in the marketplace. You should find it. It's right here. To have some syntax highlighting for the custom syntax of Omni. So as I said, we start with the ins and outs block. So we want to have one input controlling the frequency of our sinusoidal oscillator. We want to have the default value to 440, the minimum value to 1 Hertz, and the maximum value to 20,000, for example. We want to have one output. Actually, the ins and outs block are not mandatory. The only block that's mandatory here is the sample block. All the other one will be defaulted to something. In this case, they will be defaulted to ins 1 and outs 1. I'm just going to express it for clarity. So, how does a sinusoidal oscillator work? Well, basically, the way it works is that you create a phasor, which is a ramp that goes from 0 to 1 over a specific frequency time. And then you want to take that ramp and take the sine, well, times 2 pi, and then takes the sine of it to create a full circle. So to create a ramp, we need to have, some state that we can update every sample in order to create the actual increase of the ramp. So let's declare a variable called phase. Then here we're going straight to the sample block because we don't need a perform block here. We just operate at the sample level directly. So I can just use the sample block. So here we want to calculate our frequency increment, which is how much are we adding each sample to our phasor in order to reach 1 at a specific frequency. So we take the frequency and divide it by sample rate. Sample rate, of course, as I said, is the number of samples per second. So if we divide the frequency by that, we're getting a little value that added sample rate times, so over a second, is going to give us that frequency. Then we want to, of course, output out stuff. So one thing I didn't mention is that there are some inbuilt variables in Omni. Here you see in1, it's the inbuilt variable to refer to the first input. Sample rate is another important variable for, it expresses the sample rate of your system. Then out1 is the same thing as in1, but it points to the first output. And then, as we said, we want to calculate the sine of our phase times 2 pi. And our phase, 2 pi is another inbuilt variable, by the way. Our phase is going to go from 0 to 1 at a specific frequency. So we're going to increase that with the frequency increment, and modular around 1, right? So we compile that with the Omni compiler. What we get out is actually two things. One is a shared library that contains all our code. Another one is an header file that contains all the entry points for that shared library. I just want to say that Omni can also compile to static libraries, so this is the same thing. It depends on what you want to use. So Omni has different entry points, as I said. The first thing to mention is that how does Omni allocate memory? Well, it's actually up to the wrapper that implements Omni. By default, Omni allocates memory using malloc, realloc, and free. But when you initializes an Omni shared library, you can actually pass in pointers to your own custom allocator functions. So you're not stuck with something. You actually are given the possibility of embedding Omni anywhere this way. And this is the same thing for the print function. You might have your own custom function that prints stuff out, but you want to still print stuff from Omni to that. In Omni, your print function will print. So here we might want to print phase as soon as we init the code. And this print function, as I said, defaults to, I didn't say actually, but it defaults to printf, the C standard printf. But you can have a pointer here to another print implementation of your likes. So what are the entry points though for the actual Omni code? Well, they're here. So here we have some kind of stuff regarding number of inputs, name of inputs, default values, name of the outputs, number of outputs, etc. Here, those are the actual functions you're going to use to get the Omni code to actually process audio. So these first functions here are actually the same thing. Well, these functions here are the same thing as this. What this function does, Eugen alloc init, is allocate memory of your object and initializing anything that you might need for it. This 32 and 64 difference is due to the fact that you have the possibility in Omni to have your algorithms to either run at single or double floating point precision. Here, Omni Eugen alloc and Eugen init 32 and 64 are the same thing as Eugen alloc init 32 and 64, but just split into different functions. This is why you might want to allocate your memory somewhere and then initialize it at a later stage, and Omni just wants to give you, it just gives you the possibility of being as flexible as you want, but you can just call the first one, and it depends on your use case actually. Down on the bottom here, we're actually the core, the actual stuff that will make sound is the Omni Eugen perform 32 or 64, again due to the floating point precision, which is going to take the allocated memory that you allocated with this other function, and then pointers to your inputs and outputs buffers, and then standard Eugen free, Omni Eugen free to free the memory of your object. Actually, this Eugen code is as simple as just allocating it, calling perform over it, and then freeing it when you're done with it. That's it. That's all you need. All these other things are to make it work better in different environments. So now that we introduced a little bit this concept of wrappers and environments, I want to show you one wrapper that I wrote, which is the Omni Collider wrapper, which takes Omni code and all this stuff and just wraps it to make super collider unit generators. So unit generators in super collider are the building blocks for you to build your synthesis engine. So this way you're basically allowed to compile your Omni code to super collider. As I said already, what I wanted to do here is that I don't want Omni to be the one thing that exports to a multitude of stuff. I want Omni to be as simple and minimal as possible, and then you write wrapper around it for your own specific projects. In this case, I use Super Collider, so I wrote a wrapper to output Omni code to Super Collider. I also wrote one for Max MSPs called OmniMax, but here I'm on Linux, so I cannot show Max since it's Windows and macOS only. So yeah, we got Omni Collider installed. So instead of calling the Omni compiler, we're going to call the Omni Collider compiler. What it's going to do is compile the same Omni code and build a unit generator for us and put it directly into the Super Collider extensions folder, which is where you put all your Super Collider plugins. So once we are in Super Collider here, I'm rebuilding Super Collider. Let's put the synthesis server. Also, one thing I have to do is connect the output of Super Collider to the input for the recording system. So our OmniSign code will be here in Super Collider, and you see the parameter we expressed, frec, is there with that default value. So let's play that out in stereo. It's gonna be a boring sine wave. Let me just check the phonemes a little bit so I don't blast your ears. Yeah. Right, we got a sine wave. We want perhaps, and this sine wave, of course, is Omni code running in Super Collider. It's been compiled down to what Omni does is compile Omni code to nim code, which then is compiled to C code, which then is compiled, of course, to static, like native binaries. There's no runtime here. It's all compiled, and it works idiomatically with the system you're using, in this case Super Collider. So let's control the frequency of the oscillator with the position of our mouse, for example. Yeah, that should be it. Yeah, and see down here, actually that's the thing I was telling you about. This is the print function we used earlier in our algorithm here. And this is actually redirected to Super Collider's print debug window, post window, through a simple pointer to the print function in Super Collider, which is expressed in the Omni Collider wrapper. It's as easy as that. So let me just check how much time we have here. 25 minutes in. We have a little bit more time, but I want to talk about a lot of things, so I guess we're gonna jump into a little more complex example. Let me close all this stuff. So this is the implementation of the delay that I was showing you earlier on the slides. So here, what do we have here? It's a simple delay where you have 4 inputs. So the first one is your actual signal that you want to delay. So what's a delay? A delay is basically a repetition of your input signal at a specific time. The time is expressed as a delay time parameter here. Then you might want to have some feedback. Feedback is basically taking the output of your delay and feeding it back in. So it creates this kind of trail of sounds. We're gonna hear about it in a second. So here in the init block, we're actually allocated some memory for a delay struct, which is an inbuilt struct of Omni. We're gonna talk about structs in a second. It's an inbuilt struct that allocates memory for your delay line and takes care of, things like interpolations and stuff like that. So in the sample block, in fact, we're actually unpacking the variables out from our inputs. All of this stuff here is going to be removed at some point, where the name of a input will be automatically defaulted to its input correspondent. But here I'm just declaring variables and unpacking the input. I could just ignore this and put this in like this instead. So here we're actually reading from our delay line. We're outputting that out and mixing it with the input signal, and then we're writing back to the delay line down here. So this read and write value and write functions are actually called defs in Omni. And this actually implement what I was saying about interpolators. So here is a simple implementation of a delay line that if we compile this with Omni Collider, again, it's gonna output the Super Collider. I've got it compiled already, so I don't have to reboot the Super Collider server. But what you can hear here, let me copy this maybe. So we're having a signal here, which is a simple sine wave, but triggered once per second with a little envelope. So it's a little percussive sound, once per second. Let me check the volumes for this. Okay. Yeah, not that exciting, but if you apply a delay to that, that happens 1 per second. If I apply a delay, you see the parameters of half a second in this case, with no feedback, what we're gonna hear is actually a doubling of our signal every half a second, right? Because we're gonna hear the original signal at 0.0, then the repeated signal at 0.5, and then again at the end of the second, at the start of the next second, we're going to hear the original signal again, etc., etc. So we're actually doubling what we happen. When we introduce feedback, something interesting happens. Feedback creates a trail of repetition. So for example, if we have a delay time of 0.1, which would be 100 milliseconds, and a feedback of 0.9, it means that every repetition is going to decrease amplitude by 0.9, decreasing its value and creating this kind of trail of sound. So this creates this kind of effect, and if you get shorter, you're actually going to have different pitches arising, because the delay is going to be so fast that it's actually going to create pitches. So I hinted about structs, right? So what is a struct in Omni? Well, a struct in the top here is basically like a nim object, but where all its memory layout and allocation and way of allocating with the custom memory allocators that you can pass in are automatically handled for you. So a struct, the way you define it is with a struct construct. You give it a name, and then you define the fields of it. In this case, this myDelay struct has 2 fields. The first one is called delay, of type delay. The second one is called prep value, of type float. In Omni, when you don't specify the type of a field struct, yes, it's going to be defaulted to float. So this is actually identical to that. Then here we're actually defining a def, which is Omni's way of defining your own functions. And this def is actually just going to create us an object of myDelay type. And the 2 arguments are actually the two arguments are actually the initialization of the two fields of the struct. So here the first argument will be a delay, so we create a delay, and it's going to be set to delay here. And the second one is a simple 0.0, which is going to be set here. Then process, right? We're defining a def called process to actually process our audio algorithm. What we're doing here actually, and I'm hinting about it, we're actually abstracting out all the complexity of our algorithm into a secondary file. So here, this was our original code, omni-delay.omni, where everything was allocated and dealt with in init and sample blocks. What we're doing here in this other code, so using this require statement at the top, where we're requiring other Omni code. So we're basically modularizing our code, and then of course we're still declaring inputs and outputs, but then, well, no outputs here because, as I said, it's defaulted 1. But again, here in the init block, we're just calling that one function that's the entry point that the developer of this mydelay.omni library might have given us, which is, new mydelay. It just creates a new delay line. We don't have to worry about the implementation of it if we're just taking the code from someone else. We're just creating it, and in a sample block is as simple as, for example, the guy who developed this code has a process function that just takes, some values and it spits out some other values. So you don't have to worry about the details of the implementation of it. You can actually reuse code developed by you or others and actually structure your code better this way. So this is actually the code you're going to compile, 14 lines long, to have a fully functional delay line with actually damping as well, which is a low pass filter in your feedback line. So it creates kind of an analog delay. And in 14 lines you have that implemented because you're requiring perhaps code, you're importing code. Require is very similar to nim's import from someone else that developed this code. And again, it doesn't end here because it can get as complicated as, for example, allocating a multiple of delays with a simple call to, someone might have developed a library that creates a certain numbers of those same delays, and then you have them available in your sample block right away. So for example, this mydelays.omni is the next step of complexity of what we're doing. In this other code, we're requiring the same old mydelay. Then we're declaring a new struct called mydelays, which is gonna store actually an array of type mydelay. So data is Omni's way of dealing with arrays of type mydelays. And then here we have buffers. So what are buffers? Well, buffers are Omni's way of using externally allocated memory. Buffer are only defined for wrappers. So this buffer, for example, here, if I compile it with the Omni Collider compiler, is gonna work directly with SuperCollider's interface of buffers. Buffers are gonna be allocated in SuperCollider directly. And buffers are chunks of memory. Think about them as array, allocating it, in this case, in a specific environment like SuperCollider or MaxMSP. But then the same code will compile to Max as well, because I wrote an OmniMax wrapper that deals with buffer. So buffer is a struct that is defined at a wrapper level. Omni doesn't know directly about buffer. So here we're actually storing pointers to those buffers, and then we're using those buffers allocated in SuperCollider to retrieve their values and use them, for example, to express a delay time for one of our delays. So we might have we can perhaps allocate I don't know, let's allocate 40,000 as much as our CPU handles, and then we can index each one of these with the externally allocated buffers in this case, as long as you as a developer of a wrapper, you define a buffer interface. And here again, what I want to stress out is this modular approach where, this code is actually quite simple. The process is literally just looping over the delays and calling the delay process that we saw before from mydelay.omni for each specific delay, passing in the value retrieved from the buffers, right? And then we're just scaling the value out, not to blow our ears. Okay, let me check time. Okay, it's wrap up time, but I wanted to I have a lot of more things to talk about, and more examples, but I just want to stress out mainly how Omni not enforces but encourages people to develop reusable pieces of code and just have this modular approach to the way you structure both your Omni code but also your wrapper code. Because here, as I said again, buffer stuff is a wrapper level kind of thing. So maybe the buffer interface for one specific project of yours is completely different from the from the supercollider one, but you're still gonna use the same syntax here, as long, of course, as you implement it correctly as a developer of your own wrapper. But it's a sort of a write once, and then as an Omni user, you just take advantage of it. You just compile everywhere. One little thing about buffers is that every buffer will take one of your inputs away. So for example, here, delay times, we don't have minimum or default maximum values, or these ones are actually taking up one of our spaces for our inputs. So delay time is actually a pointer to a buffer that's going to express as the input. So in supercollider, for example, was Omni delay 5 here. I think I have it here actually. Yeah, it's the same. So here, for example, let me have a simple signal perhaps. Bulls.ar. So for example, we allocated four supercollider buffers of length 4, which is the same that we allocated for our Omni delay 5. Then you should just hear clicks here. But then if I randomly change the parameters, I'm basically changing in real time the parameters of our delay line. So if I'm playing, for example, some sound through that, you can hear all these trailing sounds are actually the 4 delay lines running, and here I'm just changing the parameters of all of them as they go. Let's have it super short, for example. It's gonna sound closer, but if you have it longer delay lines, it's gonna be more like a reverb kind of effect. But this is just to show the reusability of code and how you would compose Omni code. So sorry for the too long excursus. So one thing is that if you want to check more stuff and documentation about Omni, feel free to check this website right here. Here we got more stuff talking about specific things, also talking about things like generics and stuff like that, which I didn't have time to look into now, but feel free to look at that. So future work for Omni, main thing would be to develop an hot code reloading or JIT compiler kind of thing, so that you wouldn't have to run the Omni compiler every time, or the Omni Collider, Omnimax, or whatever. You would just develop your code and that will be recompiled every time you make changes to it. Also, it would be good to have like WASM compilation, so it will work. Omni will work on the web. Then Omni test would be great to test algorithms on the fly, and that links together with the hot code reloading and stuff regarding DSP like oversampling and FFT and other things. Thank you very much. I mean, I tried to put. There's a lot to talk about still, and I mean, it's a young project as well, so there's a lot to talk about and a lot to implement still. But I hope I said something that interests people. For any questions, again, feel free to write me at my email again, which is right here, or at my GitHub account. And thank you very much for tuning in, and I'll see you later. Thanks.